I'll write down this definition. Okay. If you have x not belong to capital X, this is a limit point. This is a limit point. This is a limit point, or is a limit point of capital A if and only if every open neighborhood, every open. Let me move this box. No, it's not moving. Okay. If and only if every open neighborhood of capital A intersects capital if and only if every is tilted. Okay, if and only if yeah. Am I sure? Are you able to see? No, the yeah, it has come. 1 minute. Here I am. Oh. This was. Am I right? Okay. This thing. Go back. Whiteboard. Which one I am using? I don't know. Okay. No problem. I'm explaining this. Yes, I'm getting confused. Okay. I have taken a point x naught in capital X, and this is the limit point of capital A. If and only every open neighborhood of this should be here small x naught of x naught intersects capital A at points other than what? Can you tell me? X naught belonging to capital X is a limit point of capital A if and only if every open neighborhood of x naught intersects capital A at points other than x naught. Okay, so this property is called limit point, right? Limit point property. Okay, or you may call it definition. For example, right? This is 0. This is 1. Okay, on the number line R. You take this. You take the usual topology of Euclidean topology of modulus metric. Okay, this metric in the matrix induced topology. In this metric induced topology, you take the sequence of 1, and then half, and then 1/3, 1/4, and so on. You take this sequence 1, 1/2, 1/3, 1/4, and so on. Okay, for this sequence, I'm taking the sequence of 1 by n. Okay, that is my set capital A. Okay, where n varies from 1 to infinity. Okay, capital A is this infinite set, right? For this set, 0 is a limit point. In fact, it is the only limit point for this set. Okay, how? For this 0, you take any open neighborhood. Open neighborhood consists of open intervals. If open neighborhood consists of open interval, every open interval becomes an open neighborhood. Okay, in this open neighborhood, okay, after sufficiently, if you take n sufficiently large, so all corresponding 1 by n's should be inside this open neighborhood. Okay, so this is your capital A, and 1 minute. Yeah, this is your capital A. The red points form capital A, and we are showing that 0 is a limit point of capital A. The 1 by n's, that is, if you take n equal to 1, it is 1 by 1, that is 1. If you take n equal to half, if you take n equal to 3, it is 1/3, and so on. So your capital A is this. Okay, and for this set, 0 is a limit point. Because if you for Gino, if you take any open neighborhood, how small an interval around 0 is taken, that consists of infinite number of these points of capital A. Okay, so every open neighborhood of 0, x not equal to 0, intersects capital A at points other than 0. Okay, that is why 0 becomes a limit point of capital A. Okay, so and that is an example of a limit point. Okay, to understand it better, right? If you take some, this sequence, if you take your set capital A to be this interval, this interval, maybe this is 2, this is 3, this is 5. This is open interval 3, 5. That is my set capital A. Okay, that is my set capital A. This open interval is my set capital A. And for this set, this point 2 is not a limit point. This point 2 is not a limit point. Why? I'm saying 2 is not a limit point of capital A. But now capital A is this. I'm saying 2 is not a limit point of capital A. 2 does not belong to derivative set of A. Why? Around 2, you can find an open neighborhood, small enough open neighborhood, such that this open neighborhood does not contain any point of this open neighborhood, this set capital A. Okay, so you can find a small delta around 2, such that a small delta neighborhood around 2 means you can find a delta positive, such that 2 minus delta will be this one left hand point. This will be 2 plus delta, and then right. So for this delta, so there exists a delta positive, such that this open neighborhood 2 minus delta, 2 plus delta intersection capital A minus singleton 2 is empty. Okay, so here what we are saying, every open neighborhood of if a point x naught is to become a limit point, each of its neighborhoods must be intersecting capital A at points other than x naught. So okay, what is the negation of this? There exists an open neighborhood of x naught which it does not intersect capital A at points other than x naught. Okay, so you can find for example, your delta can be between 2 and 3. You can pick up a number. That is, if your delta is less than 1, and a positive number, then this kind of open. So for this kind of an interval, okay, the intersection of this and this one will be right. This in fact is what the intersection of open interval 3, 5 and singleton 2 is. What this is, right? If this is difference set, this is capital A itself, okay, and the intersection of red interval and blue interval is empty. Okay, so this is what this is in fact is negation of this statement is a negation of. Okay, in fact there exists this delta. If you take delta to be less than 1 and greater than 0, so there is at least one delta satisfying this property. So that's why this is negated. Therefore, your 2 is not a limit point of this open interval. Okay, your 2 is not a limit point of this open interval. So that is the concept of limit point. Okay, for example, for closed interval, for this open interval, in fact, for this capital A, each interior point becomes a limit point. Each interior point becomes a limit point. Okay, and these endpoints 3 and 5 also become limit points. In fact, you can show that derived set of capital A. If my capital A is this, okay, so for that derived set is the closed interval 3, 5 for the right. So for so this is the thing. Now, in fact, now you have this situation. This contains capital A. This contains the open interval 3, 5. This closed interval. For any open interval, it's a closure. This becomes closure. It contains this open interval. Okay, and further here you have derived set of A contains this. Okay. Yeah. Now for this particular situation. So that's a little about limit points. Now, in fact, yeah. What is A closure? Can you recall what is A closure? Just I want to recall the definitions because it has been so many weeks since we met. Like last week we met, of course. So just I want to recall. How did we define A closure? Do you remember? Anybody remembers how we defined A closure? A closure is defined to be intersection of all F's where F are supersets of capital A and F's are closed. Anybody remembers? Hello? 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 Is there anybody?
Yes, sir.
Please, you said who said or no. Okay, so that I yes, I think there is one no. When somebody is saying a story, you should be saying woo. Otherwise, I don't know whether you have gone into sleep or something else. Okay, yeah. Now, A closure is intersection of all closed supersets of capital A. Okay, this is how we define. In fact, in any topological space, okay, intersection of any number of closure sets is closed. That's how your A closure becomes closed. Okay, if you have a topological space, union of any number of open sets is open. That is one property of a topology. Okay, and for right, union of any number of open sets is open. If your G lambdas are open, and if your G lambdas are coming from tau, then union of all of them is open. Okay, this also is in tau. Okay, and what is the complement of these intersections? And the complement of open set is defined to be a closure set. So intersection of any number of closed sets becomes closed. Okay, that's how a closure becomes a closure set. Now let us come to the part B. Question number 1B that says A is closed. Prove that A is closed if and only A contains derived set of A. Okay, this is right. You have this situation. Sorry, you have this situation. A is a subset of capital X. If you are inside a topological space, capital X, and A is one of its subsets. So that A is closed if and only if it contains its derived set. Okay, let us prove this. This is true in any topological space. Okay, yeah. First, let us prove this part. Let A be closed. Let A be closed. Okay. Now, how can we show that A contains derived set of A? How can we show that A contains derived set of A? A is closed. So, in 1A, what did we prove? In 1A, we showed that A closure is equal to A union derived set of A. A closure is A union derived set of A. This was done in the first part of this question, 1A. This I did the last class. If you take the union of A and its derived set, then it becomes A closure. This we proved. Okay. Now let us use this. Now A is closed. So this for any set, if you have a closure set, then you get that A is equal to A closure. Okay. If you have closed, right? If your A is closed, you have A equal to A closure. Why? Because of this. Because of this. Okay. If your A is closed, you can take A to be one of these F's. A always contains A. It need not be a proper superset. This F need not be a proper superset of capital A. It can be equal to also. Okay. If your A is closed, if you can take your capital A is containing A, and because A is closed, this is one of these F's. So you can take A here. And the intersection of these sets will be subset of constituent set. So one capital A can be taken for one of these F's. And therefore, this intersection being contained in each F, so this will be contained in capital A. That's how you get A closure is contained in capital A. Okay, if your A is closed, you will get A closure is contained in capital A. And A closure, and each F contains A. So this intersection also contains A. So you have A closure sits between A and A. That's how you get A equal to A closure. Okay, so if your A is closed, you get A equal to A closure. Right? Now, what we are showing that this is A union derived set of A. In fact, yeah, in the last class, I showed that A closure is A union derived set of A. So for A closure, you can take A union derived set of A. So what does this mean? If you take the points of D of A also, if you join the points of D of A to A, those of A, it still remain A. None of these limit points goes outside A. Means every element of D of A must be contained in A. Okay, this implies D of A is contained in A. Okay, no member of D of A can go outside A. No member of D of A can go outside A. If you take any element here that has, because of these equalities, if you take any element here, that should be a subset of an element here, means this is subset of A. Okay, that's how that's how you have if A is closed, A contains derivative set of A. Okay, converse. Let us look at the other part. Let us assume this and derive this. That is right if part. So let A be containing derived set of A. Claim what we have to show. We have to show that A is closed. Okay. So now before I assumed this and prove this. Now I will assume this and prove this. Okay. Now let A contain its derivative. A contain derivative set of A. A contains derivative set of A. Now we have to show A is A closed. So A is closed if and only if A equal to A closure. Here, if your A is closed, I showed A equal to A closure. Okay, and conversely, if your A is A closure, right, and the closure being intersection of closure sets, it is closed. Okay, the other part is very easy. Your A closure is different to be intersection of supersets, super closure sets. It's intersection of closure sets, so that is why it's closed. So A is closed. Okay, so this is equivalent. So we'll be showing A equal to A closure proof. So we have A contains derivative set of A. So what can you say? Right? If this is your A and if this is your B, right? Let this be. Let your B be red colored. So your B is containing A, right? Then what is B union A? It is right. What is B union A? If your B is subset of A, what is B union A?
A.
Okay, we have shown that A closure is equal to A union derivative set of A. Now let us use this property that A contains derivative set of A. Okay, so A contains, this is our assumption, A contains derivative set of A. Okay, so this is subset of this one. This is subset of this one. So this implies that A closure is equal to A union derivative set of A contains, right, is equal to A. Okay, it is like B is sitting inside A. This is your B. This is your B. This is playing role of B. B union A. Your B is sitting inside A. Right? Your B is sitting inside A. You call this B. Okay? And your B is sitting inside A. So you're going for B union A. If your B sits inside A by Venn diagram, right? There is no element in B which is outside capital A. Okay? That's why, whichever elements are in B, each of them is in capital A from this picture. That is what is meant by B is contained in A. Therefore, when you go for the union, it is a larger set. That is a superset of this. That is capital A. Okay. Now, because of this union becomes A. So you have that A closure is A. So this is true. So your A is closed. Okay. This is by definition. This is intersection of closure supersets. This being intersection of closure sets is closed. So that's how A is closed. A is closed since A closure is intersection of closed sets. Is an intersection? A closure is an intersection. It's a particular intersection. A closure is an intersection of closure sets, and hence it becomes closed. Okay, so your A closure becomes closed. That's why your A also becomes closed. So once you have A contains DA, your A has to be closed. So that's how closure is equivalent to saying that no limit point of capital A goes out of capital A. If a set is closed, each of its limit points must be a member of capital A. Capital A is very strong. Closedness means this capital A does not allow any of its limit points go outside of it. It means it go into the complement. It holds in it each of the limit points. That's how closedness is a kind of strength. Okay, it's strength in terms of right limit points. It is strength in terms of the limit points. Okay, closedness is a strength in terms of the limit points. Okay, yeah. Now let's look at 1C. What is 1C? We don't have soft copy. I don't have hard copy also. Okay. Let me look at 1C. Yeah, 1C is this. Yeah, that Actually, the things 1A, 1B are given as part 1 and 2 in 1A, and 1B is this 1B. We may call this 1C because I already used it 1B. So let me go for 1C. So let X be countable. Let X be a second countable space. The second countable space, right? Then prove that every open base. Then prove that every open base of X contains a countable open base, open base. Okay. Let X be a countable space, a second countable space, right? Then prove that every open base of capital X contains a countable open base. This I did last time, I think, like in one of the previous classes, but now I'll try to brief the idea. Okay. So you are inside a topological space, right? And you have, then prove that every open base. Let us take an open base. Right? G lambda, right? Let this be script B consisting of consisting of sets G, G1, G2, right? Script B is a collection of taus. I am taking topology tau on capital X. I'm taking topology tau on capital X. Let X, tau be topological space. Okay. And further space, I am taking an open subcollection, a collection of open sets from tau. Okay. And I'm assuming B is equal to, it is collection of open sets, G lambdas. So let lambda vary over script lambda. Okay. This be a base for tau. For tau or X, you can write anything. Okay. Right. Now, for this topology, you take an open base. Let it be consisting of sets G lambdas, where small lambdas vary over big lambda. Okay. So these are sets G1. The points in script B are sets themselves, right? So G1, G2, and so on. Okay. Now, what does the second countability say? We are taking X to be a second countable space. What does it mean? So there exists a countable base. There exists a countable open base. Okay, there exists a countable open base. Let me call it script B1. So second countability means this topology has got a base which is countable. Okay, here, so it consists of so many sets which are all together countable. Okay, so I'm taking B1 to be such a one. So let me put it. X is second countable. Means what? Implies there exists a countable open base script B1, okay, equal to, let me put this consisting of capital B1, capital B2, capital B3, and so on. Okay, Bn and so on. Okay, these are countable. I can take them to be like this, containing tau. Okay, X is countable. Second countable means there exists a countable open base. There exists an open base which is countable also. Okay, so that is saying, so there exists a countable open base this for tau, of course, for tau or X. Okay, now this open script B1, this is countable, and this script B need not be countable. Here in this question, what we are asked to show is that that out of these if this is countable, it's okay. If your script B is countable, it's okay. If it is in case uncountable, you can get rid of the uncountable number of things. And out of this, you can take only countable number of things. And still, you can retain script B to be a base. Okay. So countable number of things are more than uncountable number of things. So out of this, you can do a kind of haircut. You can remove all the hair of uncountable things. Uncountable number, right? The sets uncountable in number from this, removing that hair, and whatever remains, whatever sets remain, and they're all countable in number. They retain the property of script B to be a base. Okay, so this we do like this. Now we are saying this script B1 is an open base, and this script B is also open base. So if you take a set here, G1, each set here is open. So this set can be written as union of these sets here. Okay, so you have this situation, right? So for each G lambda belonging to script B1 and lambda belongs to capital lambda implies G lambda is equal to union B I lambda, where I equal to some 1 to 30. Okay, right? Sometimes this, right? Yeah. Sometimes this may be finite also. Okay, this need not be infinite. Collection of infinite sets. So, okay, the point is, right? Each G lambda, this is script B is being a base. It's an open base. So each element of it is an open set. So G lambda is open. If you take an arbitrary element of script B, it is an open set. And script B1 is also a base. Script B1 is also a base. So this open set can be written as a union of some of these. So sometimes this sum may be infinite or finite. Okay, that's what I mean by this. Sometimes it is enough to take a finite number here. Okay, yeah. So I'm writing this as union of BI lambdas, where BI lambdas come from script B1. Okay, these BI lambdas are coming from this open base. Okay, yeah. Yeah, now we proved one theorem called Lindelof theorem. Lindelof theorem. What does it say? Can anybody remember? Harshvardhan? Is he present, Harshvardhan? Can anybody remember what is Lindelof theorem? You can see it in the book and tell me. What does Lindelof theorem say? If in a second countable topological space, if you have an open set. Yeah. Hello? Hello.
Non-empty open set G in X represent union of class.
Hello.
Non-empty open set G in X is represents union of class G.
Yeah. If you have an open set which is written as a union of set number of sets, it can be shrinked to countable number of the open sets, right?
Yes.
Like every open set can be written as, if it is a union of certain number of open sets, it can be shrinked to union of countable number of them. Okay, because of second countability. 1 minute. Here, what I'm doing. Now, what is my aim? Yeah, out of this, I have to take a chop off uncountable number of things. So, yeah, 1 minute. No, I should go the other way around. See, for G lambda, I'm taking for G lambda, each G lambda can be written as union of BIs. Let us do, if we do it other way around, see, what does Lindelof theorem say? Lindelof theorem says every open G contained in X, if G is equal to some F lambda, union F lambda, okay, where lambda belongs to some eta, right? F lambda coming from open sets, okay? If you have an open set which is written as union of certain open sets F lambdas, then G can be written to union F lambda I, where I equal to 1 to 30. Okay, where these lambda i's come from eta. Sorry. So if you have an open set which is written as union of certain number of open sets f lambdas, and because of second countability, out of these open sets f lambdas, you can take only countable number of f lambda i's, such that their union is G. So every open collection, if in case this is uncountable, out of these you can remove countable number of things, and only out of these you can remove uncountable number of things, and only you can take countable number of these, and still their union becomes G. That is called Lindelof theorem. Okay. Now let us use that. What I do is I have taken wrongly. I have taken an open set in G lambda. Then I am trying to write G lambda as union of this. Let me do it the other way around. If I do it the other way around, what happens? I will take a B lambda or B eta from, rather B eta or B gamma. Let me go for a B gamma from script B. I have taken an open set in this base, and I have written it as union of these members. Let me do it the other way around. Let me take an open set here and write it as union of these members from script B. So I'm taking some B K from here, okay, from script B1. So I can as well take it because it is countable. Because my B1 is countable, I can take BK here, okay. So for a natural number, BK belongs to script B1, right? This is base, and script B is also a base. Script B consists of union G lambdas, such that lambda belongs to script lambda. Okay. Now this is an open set, right? This script B1 is contained in tau. This is form of open set. So this is an open set. This also can be written as union of these members because this also is a base. Okay. Script B is also a base. So this implies that BK is equal to union G K lambda, where K lambdas come from script lambda. Okay. So this is an open set, and this is a base consisting of G lambdas. So this open set can be written as union of some of these. I'm calling them GK lambdas, where K lambdas vary in script lambda. Okay, there exist K lambdas in script lambda. Okay, right? now apply Lindelof's theorem. Now this open set is union of these open sets, and Lindelof theorem gives you, because our space is second countable. So this open set can be written as countable number of these, countable number of GK lambdas. Okay, so I can take here union G K GKI, right? GI lambdas. Okay, let me put GI lambdas where I equal to some 1 to infinity. Okay, where right? I lambda equal to K lambda. Okay, for right, I lambda equal to K lambda. Okay, right, belong to script lambda. Now out of these GK lambdas, you can take only countable number J lambdas, where I equal to 1 to infinity. So these GA lambdas, right? These suffixes I lambdas are some of these K lambdas. Okay, these I lambdas are some of these K lambdas. There exist K lambdas belonging to script lambda. Okay, so these I lambdas coincide with some of the K lambdas. So the point is this: if in case this is uncountable collection, you can take only countable number of them. Still, the union of all these is BK. This comes from Lindelof's theorem. Okay, now each BK is writable as union of countable number of GKs or G lambdas. Okay, right? G lambdas are coming from the script B. G lambdas are coming from script B, where GI lambdas, right? GI lambdas are coming from script B. Okay, GI lambdas are coming from script B. G lambdas are coming from script B. Here GK lambdas are also coming from script B. GK. GK lambdas are coming from script B. These are coming from script B. Okay. Now each open set here, as it is writable as union of countable number of open sets from script B. I have taken an arbitrary open set here. I could write it as a countable number of open sets, GI lambdas coming from script B. I have taken an arbitrary open set here, that is BK. That is writable as countable number of open sets, GI lambdas from script B. Right? So you look at this collection, G dash, right? You collect all this BK, all these GI lambdas, such that, right? You can call this one. Okay. GI lambdas are as in one, and let your k vary over script lambda. Okay. Let your k vary over this set of natural numbers. Okay. And for every open set in this base, in this countable base, is a union of countable number of these from script B. Okay. Every element here is a union of countable number of elements from script B. So those are GI lambdas. So right, and you let your k vary. This I lambda may depend on k. I lambda may depend on k. So as you vary k, your I lambdas may vary. So collect all of them. Now here you have two indices. One is that I is one index, and the other is that k. So k is countable and I is countable. So that's how these are countable. Okay. So here you have two indices. Your I is varying and right. Your I is varying and k is varying. So this becomes countable. So, okay. That's how this is countable. This is countable. If you take this kind of GI lambdas, countable, and because because your script B1 is base, and each open basic set here can be written as countable elements from this open base. Okay, and because the script B1 is base, if you take this collection of GI lambdas, this also becomes a base because your script B1 is a base. Okay, that's how this becomes a base also. And these GI lambdas are coming from your script B. Okay, and this will be subset of script B, or rather script B. Rather, it's not G, it's script B. It's script B. Okay, Each GI lambda is coming from B, script B. So this is a subcollection of script B. So that's how this subcollection becomes countable. Okay, right? So that is the basic idea. So this you don't need. I'm sorry. You can delete this. This I don't need. You have to do it the other way around. Right? Right? So you are inside a countable space. It consists of a countable open base. Say it is script B1, and you start with a general base script B. Okay, and we have to show that this can be shrunk to countable base. Okay, how you take a basic open set here, or an arbitrary basic open set here that can be written as union of elements from here, and by Lyapunov theorem, this arbitrary open set from script B1 can be written as countable number of these. And because this is countable, because each set is writable as countable of elements from script B, so the corresponding new set, this one, this G dash, it will be countable. Okay. So that's how in a second countable topological space, every open base consists of a countable base. Okay, yeah. So that's how we proceed, right? Then let's look at this one, 2B. I will come to 2A in the end. It's a kind of bit involved. I'm afraid you get confused. Okay, I'll come to 2B. Or shall I do 2A? Yeah, okay. 2A, let us continue. 2A. What is 2A? Does it, can you tell me? let F be a mapping from a metric space X into, no. It's not good. I have to look into this now. What is it? 2021 paper from your group. What is what is 2B? What is question 2? It's not 2A, 2B, it's 2. Okay. Yeah. You can look into group 1 WhatsApp group. Suppose X and Y are metric spaces, then prove that F from X to Y is continuous if and only if F inverse of F is closed, whenever F is closed, if and only if F of A closure is contained in this. Okay. Here, in this question, X and Y are metric spaces. Okay. And then F maps X into Y. F maps X into Y. Metric space means we can take a metric on that. Okay. And then prove that F is continuous if and only if F inverse of F is closed whenever F inverse of F is closed whenever F is. Okay. If and only if, sometimes it is if and only if is written as IFF, if and only if. This is if and only if. Okay. F of A closure is F of A whole closure. Okay. This I will prove. Okay. Question, solution. I brief the answer. You can write elaborately. Okay, in the last class I did this. This I did not do. This I did. How? F is continuous. You have a function from a metric space into another metric space. F is continuous. We can show that F is continuous if and only if F inverse of G is open whenever is open for every G contained in Y open. Okay. If you take an open set here, if you take an open set G here, if you look at its inverse image, F inverse of G, it becomes open. In X. Okay. If your G is open, your F inverse G becomes open. So F is continuous. This right? This you can prove. F is continuous if F inverse of G is open whenever your G is open in Y. Okay. And from after this, here our F is closed. Therefore, you have if your F is closed, whenever F is for F closed, you have F inverse of F complement. Okay, you look at F inverse of F complement. You take an F closed. So if you look at F complement, that is open. So you apply this property. So this is equal to even before that property, this can be written as F inverse of F complement. Okay. The complement, the F inverse image of F complement can be shown to be equal to the complement of F inverse F. This you can do here, theoretically. You take an element here and show that it is here. Take an element here, show that it is here. Okay. Now, this is open. By this property, this is open. Means the complement of this set is open. So this set becomes closed. That's how this becomes closed. So if your F is closed, this becomes closed. If in case you assume this, because of this property, conversely, if you assume this, then you apply this property. You assume this and you apply this property. Then what do you have? You have that this is closed. Complement of closed set is open, so this becomes open. So complement of F inverse image of open set, this open set becomes open. And if you have any open set G complement becomes F, that is closed. Okay, so that's how I proved this in one of my previous lectures. Okay, so you basically use this and that G is open, if and only G complement is closed. Okay, you will be taking G complement equal to F, right? In place of F closed, you will be taking G complement for open G. Okay, so that's how you will be proving this. Now I will prove this implies this and this implies this. Okay, so let me take this. Yeah. Now, claim F inverse of F is closed. F inverse of F is closed for closed F, for F closed. If and only if F of a closure is contained in F of a whole closure for any A contained in a capital X. See, your F is a mapping from X XD into Y, XYD dash. Okay. Is it? They have no. I'm sorry. It's those need not be metric spaces. Those are topological spaces. I'm sorry. 1 minute. Yeah, you are given to be metric spaces. No problem. Okay. Yeah. So you are given metric spaces, and yeah, and we okay, we have to show this. We have to show these two are equivalent. I'll prove this part first. Okay. To prove this two-sided implication, I'll prove only part first. I will assume this and prove this. So let F inverse of F be closed for F close. See, F inverse. So F inverse acts on subsets of capital F. So your F is coming from here. F is subset of capital F. F inverse acts on this on sets here. So your F is closed in Y. Okay, capital F is closed in Y. Now, let us try to obtain this. So let capital A be subset of X. Okay, I have to take the help of book. This is a bit involved. You have practiced very much. Okay, I'm getting confused. I'll try to explain the proof involved. Right. So then F of A, yeah, then F of A is A closure. F of A is subset of A closure. This proof is similar to the proof of this is similar to the proof of 4.3.13 on page theorem 4.3.13 on page 35. Okay. This proof is similar to the proof of this theorem. Okay. So we always have this. F of A is contained in a set is contained in its closure, right? Isn't it? How did we define A closure? It is closed superset of closed supersets of A. F close, and F is superset of A. Okay. Each F contains A. Therefore, this intersection also contains capital A. So this is always true. Whenever you take a set, it is contained in A is contained in A closure. That's what is written. In place of A, I have taken F of A. No problem. Of course, F of A will be here. If you take A here, your F of A will be here. Okay, this is taken to F of A. Okay. Now you apply in any metric space, you have this property, right? See, every metric space induces a topology. Every metric space induces a topology. So you can visual in the metric induced topology, you can speak of the closures. Okay, by this definition. So the A closure contains A. So you can apply this property A closure contains A to this set F of A. In place of A, you can take F of A. That's what I'm doing. Any set is subset of its closure. Okay, in a topological space. Now what do we have? Can we apply this? Yeah. Now from here, what can you obtain from this? This implies capital A, you take F to the other side. This is F inverse of F of A closure. Okay. You can take F to the other side. Capital A becomes subset of F inverse of this. That's what I wrote. Now, what is our assumption? Whenever you capital F is closed, F inverse of F is also closed. Now, closure of any set, here F of A, that is a closure set. Closure of any set is closed. So this closure is also closed. So in place of F, I can take F of A closure. That's how this is closed. Since F of A closure is closed. Closed, and by this assumption, and by 1, and by 2, and by 2. Okay. You take the assumption and that f of a closed is closed. So this is a closure set. In place of f, you take f of a closure, right? In place of f, you are taking this. So f inverse of f will be closed. Now, from here, what can you say? And f is continuous. Yeah. Okay. So f is continuous. What? No. This is closed. No, you don't need continuity. You don't need continuity. Continuity is equivalent to this property. Continuity is equal to this property. And then now we are showing that these two properties are equivalent. Okay, this sentence and this sentence are equivalent. So I'm here. So we have that this is closed. After this, what can you say? This implies f inverse of f of a closure is closed. Yeah, this is closed. Now this implies a closure. A closure is contained in f inverse of f of a closure. Can I write this? Yeah. Here you have got a closure. See here, if your f is a closure superset of a, then your f will be coming here. If you have a closure superset of capital A, then your capital F. If it is capital F, if you have a set capital F, which is a closure superset of A, that capital F will be one of these members, suitable members. Okay. So and this can be taken in place of this can be taken. See, what is A closure? A closure is closure supersets of these F's. A closure is intersection of closure supersets of A. Now, in place of F, I can take this because this is a closure superset. This is closed and it is also super. Therefore, right? If you from the definition of A closure, so 3 implies that A closure is contained in F inverse of F of A closure. Okay. Because this is a closure superset of A, this set will be contained in A closure because this set can be taken to be one F here, and you can take this set as one of the constituent sets, capital F here. Okay, and A closure will be subset of each of the constituent sets. That's how A closure will be contained in this. Right? Take capital F equal to. This is different. This is different. This sentence in this sentence, capital F is this, but here for this you take capital F to be for this capital F you take it to be this one. Take F equal to F inverse of F of A closure. Okay, so if for 3 you take a capital F to be this one. Okay, this F is different. This F is different. Now you bring F inverse to left hand side. What do you get? What do you get? F of this is contained in F of A closure. F image of A closure because is contained in F of A closure. So you'll get this. Okay. So this implies that F of A closure is in F inverse of A whole closure. Is it? No. F image of this contains F of A closure. You don't have inverse here. So it is. Yeah. Now the F image of this is contained in F of closure of F of A. The F image of this, you bring F inverse to this. F image of this is contained in closure of F of A. F image of this is contained in closure of F of A. That is this left hand side. This right hand side. Now we'll assume this and obtain this, right? So to prove if part. So let this part. Let F of A closure be contained in F of A whole closure for every A contained in X. Claim. What do you want to prove? That F inverse of F, right? We'll prove F inverse of F is closed for closed F in Y. Okay, we'll assume this. We'll assume this and prove this. Okay, so let us assume this and take a closed F in Y, and let's look at this F inverse F, small f inverse capital F. Okay, so yeah, now here, yeah, 1 minute. Let me copy. Yeah, you take A equal to F inverse F. So in the, to do that, what do we use? We shall prove A. Okay, okay. No. Is it? Okay, he wants to prove the other way around. He will prove that F is continuous. From here, he will prove that F is continuous. And then once he proves this implies F is continuous, right? And from continuity, he will prove that F inverse of F is F. Okay, so after that, continuity is equivalent to F inverse of F is closed for closed F. That you can do for closed F. Okay, so this I will do. F inverse of F, F inverse of F is closed. No. From once you prove continuity, continuity is equivalent to this. So you have done this. So I don't need to write this. Okay, which is, and this is, it is equivalent. Right? This is equivalent to this. So we will in fact prove that this implies F is continuous. Okay, so to do that, yeah. So let us take A to be, let A to be F inverse of F, big F. Okay, then for, yeah, so for F closed in Y, you consider A equal to F in, call this capital A. Now we shall prove A equal to A closure, that A is closed. Okay, we'll show that this is closed. Okay, that's what we want, right? Now F of A closure is contained in this. F of A closure is contained in F of F inverse of F closure. Why? Yeah. Now in place of A, see, this is your assumption. Call this 4 by 4. This is your assumption. Okay. In place of A, you take F inverse of capital F. So in place of capital A, you can write F inverse of F. So here, in fact, equality. In place of A, you can write this. In place of A, you can write F inverse of. Then what happens? You can take equality here. This is equal. So in place of A, you substitute F inverse of small f inverse of capital F. Okay. Now by 4, what does this imply? This is contained in F inverse, right? F of A closure. F of, what is A? F inverse of F, right? Whole closure. Okay. Now, F of A closure. For A, you substitute small f inverse of capital F. Okay, this you have equality here. For capital A, you are substituting this. Now, you take this hypothesis. In capital A, you write F of F inverse of capital F. Your capital A means small f inverse of capital F. So here, this left hand side is this. It's subset of F of A closure, F of A whole closure. That is closure of F of, what is A, capital A, F inverse, small f inverse of capital F. Now, what does this mean? Short. Okay. Now, what does this mean? Now, F inverse of F is now F inverse of F of F inverse of F, F of F inverse of F is always contained in F. Right? What happens is this. Your F is mapping X into Y. Your F is mapping X into Y. You are taking you are taking a capital F here, and you are looking at F inverse of small f. Okay, you are looking at F inverse of F. I'm sorry. Right, F inverse of capital F. This you are looking at. So you have taken a capital F here. You're looking at its inverse image under small f. Now, if you take the F image of this, the F images will go into capital F, because it is right, because you are taking elements, the points from the pre-images from F inverse F. So if you take the images of these points, the points here, those will have to go to this because of the difference of F inverse of F. So this is always true. For any set, this is true. Okay. Now you take closure, right? Yeah. Now you take closure on both sides. If A is contained in B, A closure will be contained in B closure. If A is contained in B, A closure will be contained in B closure. This is always true in any topological space. Okay. So in place of this, because for this you take this as A and this as B and apply closure operation. You will get this. So this will be subset of, right? This will be subset of F closure. Okay. So if you combine these two, now closure of this will be contained in closure of F, and you are taking F to be closed. Your F is closed, so F closure will be capital F. Okay, so you have obtained that F of A closure is contained in capital F. So what does this give you? Right, this is equal to this is contained in capital F. So F of A closure is contained in capital F. So F of A closure is contained in capital F. What does this give you? A closure is contained in small f inverse of capital F. Okay. You have shown that F of capital A closure is contained in capital F. So F of A closure is contained in capital F. Now you bring F to the right hand side of this. So A closure is contained in F inverse of capital F. Okay. Now what is your F inverse of capital F? It is capital A. It is capital A. So this is capital A. And this is always contained in A closure. A is always contained in A closure. And this is also contained in capital A. So from here you get A equal to A closure. Okay. So what you have done, you started with the, therefore your A is closed. Okay. From here, A closure is contained in A closure. You get A equal to A closure. So right between A closure sits capital A. So your capital A must be equal to A closure. This from here you get closedness of capital A. Now your capital A is closed, means this is F inverse F is closed. Okay. So that's how this implies that this is true. So in any metric space, these two are equivalent. This property, F inverse of capital F is closed for F closed is equivalent to F of A closure is contained F of A whole closure. This is set theoretic property. This is set theoretic property. Okay. Yeah. Now, do you want to ask any doubts or? Hello? You people are not studying, I think. You don't ask anything. You have any doubts? Hello?
No, sir. We are listening.
If you have any doubt, please ask.
No, sir. No, sir. No doubts.
पूछिए कोई शक है तो पूछिए. Hello.
And sir?
Do you have any doubt?
No, sir. No.
Everything is doubt for me. Okay. 3A. Prove that in a topological space X is compact. X is compact. If at all, yes, बताइए.
एग्जाम की पर्टिकुलर గా ఏం ప్రిపేర్ అవ్వమంటారు కరెక్ట్ ఎగ్జామ్ పాయింట్ ఆఫ్ వ్యూ లో కొంచెం ఇంత లిమిట్ వరకు ఇంత ప్రిపేర్ ఎంత వరకు ప్రిపేర్ అవ్వమంటారు?
See how many blocks you have? How many chapters you have? How many chapters are there in your this thing? 18? Huh? How many?
18 chapters.
How many chapters are there?
18 sir.
18 are there. Of course, one is the first part is fundamentals, first unit. Okay. see, you have 200% choice, right? You have 200, for 70 marks, you are asked, you are given 140 marks of questions, right? For 70 marks question paper, you are asked questions for 140 marks, okay? Means if your questions are uniformly asked from all the chapters, then if you read half of the chapters of the book, then you will get 100% marks, right? Okay, so 9 units. If you are thorough in 9 units, you must get, you are likely to get 70 out of 70. Okay.
सर कौन से चैप्टर से ज्यादा मार्क्स ज्यादा क्वेश्चंस आते सर? कौन से चैप्टर से ज्यादा क्वेश्चंस आते?
There is nothing like that. It depends on the paper setter, and of course, there will there will everything is important. Everything is important, and see, you should know the fundamentals. If you know the fundamentals, right? If you are clear with definition, see. Without understanding the concepts, basic concepts, you cannot advance. Okay. If I ask questions from the 15th chapter, you cannot, unless knowing the first chapter, second chapter, unless you know the concepts of topological spaces, which is unit 2, you cannot study anything from the remaining chapters. Okay. This is completely on topological spaces. So you should be thorough with the concepts. See, in unit 2, what are you explained? You are explained right? You are explained topology, right? You are explained topology, and you are explained open sets, closed sets, and you are explained closureness, a closure, and on this you have so many questions on it, a closure. Okay. So see, what I'm saying is, so if you are thorough in 9 units means, if your questions are uniformly spread out among all these 9 units, you are likely to get 8 marks of questions from each unit. 8 marks of questions from each unit per unit. Okay. So if you are thorough with 4 units, you are likely to pass out. If you are thorough with 4 units, you are likely to pass out, because 4 8 is 32. Pass mark is 28 out of 70. You don't aim for this one. No, it's a bad process. You be thorough in the first 6 chapters or so. Or, right, one way is this. You be thorough in units 2, 3, 4, and 6. Okay, and maybe some easy concepts will be separation axioms. Units 10 and then 11. Okay. Then it's up to you, right? If these you must know, 2, 3, 4, 6. These are fundamental. This is on topological spaces, and this is on continuous function, right? This is on open basis and subbasis, and this is on continuous functions. I avoided unit 5. If you are thorough in your real analysis, you can study unit 5 also. If you are thorough in your real analysis, you can complete unit 5 also. Even if you don't do that, even if you skip that, if you are thorough with these 4 units, you are likely to pass out, right? You have to be thorough, I am saying. Means whatever I ask from these 4 units, you should be able to answer. That's what is meant by thorough, okay? Right? So there will be, you cannot just read or mug up some questions from these and then go for exam. It's a bad way. I never advise that. Okay, see, mathematics is not like social studies or something like that, something else. It is not like story. It is not like story. Okay, you cannot mug up things. If you mug up things, you will be, what happens is your practice will be less and there will be some mistake. Instead of implies, you will be writing union, and instead of union, you will be writing implies, or so many notational mistakes will be there. So if there is any notational mistake in any sentence, it is mathematically wrong. The sentence is mathematically wrong. Okay. So mathematics needs a lot of practice. You should see here, in every time I'm writing, whatever I'm writing, I'm trying to do it perfectly. So that's why, that's how you have to practice. Even for our MSc, we used to do that. You have to practice. First, you have to understand the concept. And then you have to practice writing the statements without any mistakes. So then you will get marks. Okay. For example, in one of the previous classes, I was showing that the a totally connected space, a totally bounded space is bounded. A totally bounded metric space is bounded. A totally bounded metric space is bounded. Metric rather. Okay. Here I committed a mistake, but none of you asked me. I pointed out the mistake because you are not putting into your brain into that. Okay. See, what I am doing is, so that's how you have to study things. You have to study your things with your brain into it. Then you can pass out. If you study only a few questions from here and go for exam, if those questions don't come in the exam, then you are gone. You cannot pass out. Okay. So the point is, you have to understand the concepts. You understand the definitions, and then properly, and then examples and counter examples. Okay, examples and counter examples. Okay, and then theorems and proofs without any mistakes. So if that way you study any 4 units, you can pass out the exam. Okay, so there is no hard and fast rule that this thing should come, this thing should not come like that. If sometimes Uridan's lemma comes, and sometimes T-just extension may come. Right? So it depends on the paper setter. Okay. Even basic, if you're asked what, if you're asked simple things, you should be able to do it. Right? If you're asked, if you study Uridan's lemma, right? And if you are not able to write on what is T1ness, what is T2ness, what is CR-ness, what is regularity, then there's no point. If you just mug up, Uridan's lemma, and you are not able to understand, present these concepts, write down the definition, give examples and counter examples, then the effort, right? It's not correct preparation. Okay. So what I'm saying is, see, in the last class, in one of the last classes, I was drawing that a totally bounded metric space is bounded. How I was doing? What is a totally bounded metric space? If any epsilon is given, then there exists a finite number of open sets. Right? Finite number of open balls. Okay. We call these centers. X1, X2, X3, X4, X5, and so on. So and if you are inside a metric space, then this can be written as union of S epsilon of these open balls. These are open balls. S epsilon of Xi, X1. This is X1. This is epsilon of X2. This is for all these open balls, radii is our same, equal to epsilon. These are all epsilons. Okay. These are open balls of the same radius. So you can totally boundedness means this X can be written as union of S epsilon of Xi, where I equal to 1 to n. There exists a natural number, right? There exists a natural number n such that S can be written as these union of these open balls. Okay. Now to derive this, what I was saying that you have to take a general point here X and a general point here Y, and I said you take M to be the maximum of the distances between these, right? You go for these distances between X1, X2, X1, X2, X1, X3, then X1, X4, then X1, X5, then X1, X6, and X7. Means you are taking D of Xi, Xj, where 1 and I vary between 1 and n, right? And that, not only this, after this, you also have to take this set, that is Ri, where 1 is less than to I less than to n. You have to take these radii also, which are epsilons. Yeah, these radii are epsilons. Okay. So yeah, it is enough to take epsilon, union epsilon. What is this? That's right. Because for these radii are equal to epsilon, you can take epsilon here. Okay. So this is epsilon. So if you if you take maximum of all these, that is, let it be capital M. Then what happens? What is the distance between X and I? Then you have to take this distance. If X lies in this open sphere, then you take this distance between X and X1, that is less than epsilon. and then you take the distance between x and this center of this open sphere, that is some xn. Okay, it is this. That is right. That is less than m. That diameter, that distance is also less than m. Okay, so the distance of x comma y is less than epsilon. But triangle inequality, this distance, the distance between this point and this center will be less than epsilon, plus the distance between x1 and xn will be less than m, and and the distance between y and this center will be less than epsilon. Okay, so this is 2 epsilon plus m. If in case, first let me tell this. So that's how in the right. Yeah, and in fact, union of all these will be capital X. Union of all these will be capital X. So if you take any 2 points from capital X, the X and Y, they have to be in somehow a pair of these sets. So and the distance between them has to be less than or equal to this. And this is a constant. Epsilon is constant, but for fixed, right? You take epsilon, you put epsilon, right? Fix this epsilon naught, so you'll get epsilon naught here. So this x d of x comma y is bounded by this. So that's how your capital X is bounded. Okay, right? So the same way you can show that in a metric space, if it is compact, that is bounded. Of course, right? In a metric space, if that space is compact, you can show that space is bounded. The same lengths you can do. You take epsilon equal to epsilon. Yeah, we can start with the fixed positive number, and you will get capital X equal to a finite number of open sets, and you obtain this. Okay, so you have to understand the concepts and present properly. Okay, and then you will pass out. Okay, and if you simply try to read a few things and vomit them, it may not help you, because if you don't know, there will be notational mistakes, and whatever you write, it should be mathematically correct, right? Right? You should not write a contradicting sentence. Your sentences, statements. What are statements mathematically? What is a statement? Right? It must have truth value, true or false, but nothing else. Okay. If you write a statement, means a mathematical sentence. If you write a mathematical sentence, okay, then it must have truth value only true and false. Yeah, and your sentence must have the truth values one true or false, but nothing else. So if that is the case, whatever you write will be correct. Otherwise, it's not mathematics. Your answers are not correct. Okay. So the point is, you have to practice. First, you as I'm saying, you first understand the definitions. First, you understand the definitions, right? And then examples and counterexamples, definitions, examples, counterexamples, and then try to understand theorems.
सर understand हो रहे हैं, लेकिन बाद में और फिर confuse हो जा रहे.
हाँ?
Definitions को understand हो रहे, after फिर confuse हो जा रहे.
No. Confusion means your practice is less. Confusion arises when your practice is less. If you are not practicing enough, then confusion arises. If your practice is strong, then there will not be any confusion. See, in our MSc, we used to understand definitions and then examples and counterexamples, and then understand theorems, statements, theorems, proofs, understand proofs, memorize proofs, and able to write them without seeing the book. Okay, without seeing the book, without any mistake. That you have to practice. Then things will be clear. Otherwise, things will be in confusion only. Confusion comes when your preparation is less. In any case, your confusion comes when your preparation is less. If you are participating in a sprint, in a match, in a cricket match, if your practice is less, you will be clean bowled. Okay. If your practice is less, you can't bowl the other person. It depends on practice.
Yes, sir.
Yeah. So that's what I'm saying. See, many of you think that in the last 3 days before the exam, I'll put leave and read and write down. No, it's not correct. This is not vomiting things. As I'm saying, you cannot write things without any mistakes. I know. See, sometimes I'm committing mistakes. In the proof of this, I committed mistake. No, none of you pointed out. Okay, later on I realized this mistake. Okay, so you should be careful. You have to practice very much. Okay, then only this confusion disappears. Okay, otherwise it prevails. Okay, can I stop here? Hello. Hello.
Yes, sir. Thank you, sir. Thank you.
And if you want, we
That's
can meet till the exams are over. We can meet during weekends if you want.
Hello?
Okay, I'll be clarifying your doubts. Yes, please.
screens once more, sir.
Yes, please.
Screens, sir. Screens once I want to save it, sir. Due to some network problem, I could not join in the beginning, sir.
I'm not getting. What, madam? Say, what?
Sir, can you please show screens, sir, from the beginning, because I joined late, sir, due to some network problem.
No, today's?
Yeah. Yes, sir.
Yeah, I sure. No problem. This I can do.
Okay, thank you, sir.
From which one? From page 1?
Yes, sir.
I'll do it. No problem. That can be done. This is page 1. How do you copy? This is page 1. Can I go to page 2? Do you take photo or what? Can I go to page 2? Hello?
Yes, sir.
Okay. Are you taking photo or what? Page 2. This is page 2. Can I go to page 3? Hello? 3?
Yes, sir.
Okay. This is 3. Page 3. Can I go to page 4?
Okay, sir.
Page 4. This is page 4. Page 5. I have taken page 4.
Okay, sir.
Page 5. Then page 5. Page 6. Have you taken page 5? Hello? Page 5?
Over, sir. అయిపోయింది.
Page 6. This is page 6.
అయిపోయింది, sir.
This is page 7. Page 7. Page 8. Page 8. Page 9. Page 9. Page 10. Page 10. 11.
Okay, sir.
Okay. Okay. Have you
Okay,
got
sir.
all pages? Right. Okay. And if you have any doubt,
Okay, sir.
please see. I have given you my phone number. We have first year WhatsApp group. My phone number is 99492638663. Okay. And right. 492638663. 63863. And you can put your doubts through that WhatsApp group. Okay. And if you want any doubt to be cleared anytime, you can call us. Okay, I'll be available and I'll try to clear your doubts if I know instantly. Otherwise, I will prepare and tell you. Okay, right? And through WhatsApp group, we can meet again if you are interested. Okay, you please read, and if you have doubts and if you want to get them cleared, then I can help you. Okay, right?
Okay, sir.
Can I stop here? Hello.
Yes, sir.
Okay, sir. Yes, sir.
Anything else?
Thank you very much, sir.
Okay, so no, it's my duty. Thank you. Bye. Good luck. Bye.
Thank you very much, sir.
Okay, sir. Bye, sir. Thank you, sir.
Sir.